So with that, let me start off by, again, welcoming you to this training. This training is being offered as part of the National Hurricane Program. The National Hurricane Program is a partnership of three federal agencies: FEMA, the Corps of Engineers, and the National Weather Service National Hurricane Center. And you have three federal partners with one mission to save lives. So let's talk a little bit about the National Hurricane Program at the start. The Corps of Engineers, they have a national program managers as well as their district study managers that work with the states to help develop and manage the hurricane evacuation studies. FEMA has the national program manager, Zane Heather, who you just heard from, as well as the regional program managers that provide technical assistance to the state and local governments in support of these hurricane evacuation studies, as well as myself and Michael Spagnolo, who you'll hear more from later today, but we help to support with the operational decision support. And then as well, you will hear the first unit will be taught by the National Hurricane Center in this training. You'll hear from the Hurricane Specialist Unit members as well as the Storm Surge Unit as well. So the types of services that the National Hurricane Program supports is the operational decision support, the planning support and technical assistance. That's part of the hurricane evacuation studies, as well as training like this that we are participating in today. So a little bit more about those products and services. The National Hurricane Center provides the forecast products. The Storm Surge Unit does the storm surge modeling, and all of this gets rolled up into the hurricane evacuation studies that the Corps of Engineers and the FEMA regional folks are working with the state and locals to assist with that guidance in terms of working towards those evacuation studies. And all of that gets brought into HUREVAC, the operational forecast products, the storm surge modeling, and the data from those evacuation studies. And all of that allows for the operational support that the program provides, the planning support, as well as, again, training like this. This all leads to better decisions, informed decisions, which we're going to hear more about in Unit 4 of this training tomorrow. So the course goal today, to enable you as the participants to better plan for the hurricane threat by ensuring that you have an understanding of the hazards, the uncertainty, and the resources available to respond. And so that we're going to talk about the Hurricane Center products, as well as the evacuation studies. So some of the objectives by completing this course, we should have a better understanding of the hurricane life cycle and the climatology, and most importantly, the hazards, because as emergency managers, that is what you're actually going to be responding to. And then where you're going to get your information. The Hurricane Center produces a lot of products that are available, and they're a great resource, and we're going to walk you through how you use these and evaluate your threat from an approaching storm. We're going to discuss tomorrow the uncertainties of NHC forecasts that you need to consider. As emergency managers, you don't have the luxury of waiting until the storm affects you. You have to make decisions with uncertain information. We're going to describe the storm surge threat and how to assess your potential impacts. And we're going to explain the components of the hurricane evacuation study. And then finally, identifying the resources that are available for evacuation planning and response. So today we are going to cover the basics of hurricanes. I mentioned the climatology and the hazards. And so when we complete this unit, I'm going to hand it off to the National Hurricane Center staff. And then after they have finished, myself and Michael Spagnolo are going to talk about the use of the products. Tomorrow, we'll start all over again at 1 o'clock, and we're going to hear about forecast uncertainty and the resources that are available to help you make decisions based on that forecast uncertainty. And then the last unit will be all about the hurricane evacuation studies and how we can use all of this to make better decisions. So if you're interested in downloading the materials that you see today, that includes the student manual as well as all of the slides. If you want to go to the Hurricane Center's website, their outreach page, so that's www.nhc.noaa.gov/outreach. You can download the PDFs of all the materials that are being presented today, or you can scan that QR code. I'll give you a moment to do so if you choose. Okay, with that, I am just going to ask a couple of questions since this is a large group. We have a lot of people on Zoom, and as an opportunity for us to do a better job in terms of training, trying to understand who is in this training and get a better sense for what everyone's background is. So how long have you worked in the field of emergency management? Less than a year, 1 to 5 years, 5 to 15 years, or more than 15 years? In my case, it's more than 15 years. So far, we've got about 450 people responding. Okay. So we have a pretty good distribution here. We have about a third, I'd say, that have about 1 to 5 years, and a third with 5 to 15, and a little bit less that have more than 15 years. So we have a pretty good distribution of people. Let's go to that next slide. The next poll, I mean. So where in emergency management do you represent? So what level of emergency management do you represent? Are you a local emergency manager, a state emergency manager, tribal or territorial, federal, or other? Okay. So it looks like we have about a third of you are local emergency managers, a third are federal, and then the rest is distributed between state, tribal, territorial, and other. What is your primary role in emergency management? Do you work in plans? Do you work in operations? Are you a public information specialist? Do you work in training and exercise, or other? Plans, operations, public information, training and exercise, or other? Okay, so it looks like about almost half are in operations um, or plans and other, and a few public information specialists. We're going to talk a lot about the operational products here, but we're also going to talk about how you can use this to inform both your communications as well as supporting exercises as well. And one of our last questions, in your role, what is your level of experience with hurricanes? Are you just starting out with hurricanes? Do you have a little bit of experience, moderate experience, or extensive experience? Looks like we have pretty much a normal distribution between little to moderate and extensive. So pretty much in the middle there. And the last question. Have you ever attended a National Hurricane Program course in the past? So have you attended L311 like this one? Have you attended the week-long course that we offer here at the Hurricane Center, 8324, one of the local or state-specific courses, or the inland course or HURAVAC? So it looks like a lot of you have taken the HURAVAC training courses before. And for some of you, this is a refresher. Either you've taken the week-long courses or the in-person version of this L311. Excellent. Thank you. So with that, were there Zane, were there any questions that or things that need to be communicated before we pass this to Unit 1 with the folks at the Hurricane Center?
Hi, Matthew. Nothing raised in the Q&A box right now that has not been addressed. Just going to highlight for the participants online in the chat, you can find the links to both the materials presented, so that is the PowerPoint slides and the user guides, as well as the link for the closed captioning provided in both English and Spanish during this service. We also have sign language interpretation support, and so if you need that, I would highly recommend you pin the sign language interpreter to the top of your screen. Other than that, and pending anything else from the panelists, that's all we have. Thank you. Next up, we've got Unit 1. Back to you, Matthew, to kick it off or to help with the transition.
Thank you. Yep, thank you. So with that, I'm gonna hand it off to Andrew Hagan with the Hurricane Specialist Unit at the Hurricane Center to kick us off with Unit 1 of this course.
Before I begin, hi everybody, just wanted to introduce you guys to a couple of the hurricane specialists and storm surge unit specialists here at NHC. My name is Andrew Hagan. I'm one of the hurricane specialists. I'll be speaking to you first. We also have Larry Kelly.
Hello everyone, Larry Kelly, hurricane specialist. You'll hear from me a little bit later in Unit 1, then also Unit 3 tomorrow.
And hi, my name's Heather Nepal. I'm with the Storm Surge Unit, and so I'll talk to you about Storm Surge in just a minute. And we also have Cassie Mora.
Hi everybody, I'm Cassie Mora. I'm also a storm surge specialist, and I'll be in the background answering any questions you have.
Okay, so I'm going to bring up the presentation here. Let's share screen. I'm going to share my entire screen. And let's see. Oh yes, then I had to. Okay. All right, I assume y'all can hear me fine. Everything's good. All right, so we're going to talk a little bit about hurricane basics. I'm going to be talking with you for the first 25 to 30 minutes or so before we hand it over to the next person. So in these first 25 slides or so, you should be able to, by the end of these slides, describe the characteristics and life cycle of a tropical cyclone and describe Atlantic hurricane climatology. And I'm also going to be talking about a few other topics. And then during the next part, I believe Larry is going to talk about some of the hurricane hazards. All right, so let's jump right in. the definition of a tropical cyclone. So tropical cyclones are large and long-lived low-pressure systems. They can be hundreds of miles wide, and they could last for several days and even 1 to 2 weeks in some cases. They form over the tropical or subtropical oceans, over the warm waters. That's how they get their fuel. And tropical cyclones are areas of low pressure that don't have any fronts attached to them. If you think about mid-latitude cyclones like nor'easters, those have cold fronts and warm fronts attached to them, and they're asymmetric, whereas hurricanes are more symmetric and a little bit more circular, and they don't have any fronts attached. They, as I was just talking about, they produce organized thunderstorm activity, so they're kind of organized in somewhat of a, that kind of circular fashion. It's not just random disorganized thunderstorms. And the last thing that defines a tropical cyclone is that it has to have a closed surface wind circulation. And so these areas of low pressure in the northern hemisphere, they rotate counterclockwise. So you have to have that completely closed wind circulation at the surface in order for it to be a tropical cyclone. And talking a little bit about some of the classifications of tropical cyclones. So if you do have those organized thunderstorms about a well-defined closed circulation, then you have a tropical cyclone. But if the maximum sustained winds in it are less than 39 miles per hour, it's called the tropical depression. And if conditions are favorable and it's able to strengthen, then it could become a tropical storm once those maximum sustained winds reach 39 miles per hour or higher. And if it strengthens to a 74 mile per hour system, that's when it becomes a hurricane. Major hurricanes are categories 3, 4, and 5 on the Saffir-Simpson hurricane wind scale. And it reaches that category 3 threshold once a hurricane becomes 111 miles per hour or stronger. I'm taking a look at this satellite image of this system circled in red in the southeastern Caribbean. So, we're asking the question here: does this have a closed surface circulation? Are the thunderstorms organized? That's what the hurricane specialists are asking, because at this time, this was just a disturbance that it probably had a high chance of development in our tropical weather outlook, but we were not yet issuing advisories on this system. And so we're looking at the satellite imagery, trying to, one of the ways to pick out if it has a closed surface circulation is to look at some of those lower cloud lines. But these brighter colors over here show the deep thunderstorm activity, basically. And so, is that considered well organized enough? Well, if it kind of has, if it has a lot of thunderstorm activity that's kind of organized in bands, and it kind of is located relatively close to where that surface center of circulation is occurring, and that persists for 12 hours or more, then we consider that to be well organized. And it does look like there is rotation in these low-level clouds, like on the western edge of the thunderstorm. So, just by looking at the satellite, that might be enough to say this is a tropical cyclone. And it turns out that this was Tropical Storm Ernesto of 2006. And back in 2006, we didn't have those potential tropical cyclone advisories, which you'll maybe learning about later in this course. But we also had an aircraft in there. The aircraft was able to confirm that it did have a closed circulation. So and it also confirmed that the winds were tropical storm strength. So at that time, we issued advisory number 1 on Tropical Storm Ernesto. Now, just to talk a little bit about the difference between tropical, subtropical, and extratropical. So an example of a tropical cyclone on the left is a hurricane, Hurricane Katrina. Tropical cyclones, especially the hurricanes like Katrina, are pretty symmetric. They're more circular than than an extratropical cyclone, for example, which is on the right. Tropical cyclones get their energy, again, from the warm waters, and they're considered something that's called warm core, because in the center of the cyclone is where the warmer temperatures are, and outside the temperatures are cooler. That's what a warm core cyclone is. On the right, you have an example of an extratropical cyclone. So extratropical just means the same thing as non-tropical. It's just any mid-latitude weather system that kind of has fronts associated with it, whether it's a nor'easter or any other type of non-tropical low pressure system. And this low is probably at this time in this example, the March superstorm of '93. The low pressure area might be centered somewhere over the eastern United States. But then there's a cold front that extends from the low. You could see the linear feature with all those bright purples and blues. That's the cold front that extends from that extratropical cyclone. Now, subtropical cyclone, so subtropical storms, we do issue advisories on those, and we do have names for those. So one thing that differentiates subtropical storms is what we call the radius of maximum winds, where those strongest winds are found. In hurricanes, the strongest winds are found just outside the eye, right, in the eye wall. But in subtropical storms, they're those strong winds are a little bit significantly farther away from the center, and you have more asymmetry to the cloud pattern. For example, in this subtropical storm Anna, you have thunderstorm activity in the southern half, but you really just have clouds and maybe very light showers in the northern half. And in terms of that warm or cold core structure, you might have some characteristics of warm core between the surface and 10,000 feet, whereas maybe above 10,000 feet, there's more of a cold core structure. So we kind of call it a hybrid because it's kind of has some characteristics of tropical and some of extratropical. So because these systems can still produce significant impacts from wind and from the heavy rainfall, we still issue advisories on those. All right, so looking at tropical storm history, this is all of the everything that's in the database. So in the Atlantic, we've been keeping track of tropical storms and hurricanes since 1851, and in the East Pacific since 1949. So, 10 to 12 or 14 of these storms every year. It adds up over 170 years or so. So pretty much the entire U.S. coast from Texas to Maine is susceptible to these storms, and not just the coast, because you know that they can produce impacts farther inland, as we saw with Helene this past year. The yellow lines are where we've had major hurricanes, category 3, 4, and 5s. So this is the first poll question. So I think someone was going to bring that up, right? So the first, what month? So the question is, what month has the most activity in the Atlantic? And if you're able to make a selection, we'll give you like 30 seconds or so to go ahead and make your choice there. Yeah, I'm not able to see on my screen like how things are coming in, but I'll just give you guys another 10 seconds, just another few seconds, and then we'll anyone know if here?
September.
Okay, so
1%.
Oh, okay. So it looks like 71% of you chose September, 25% of you chose August. So yeah, most of you are very correct that December and June are definitely the not the correct answers here, because you know that hurricane season goes from June to November. September is the peak of the season, and sometimes in early August, sometimes we still have dry air kind of from Saharan dust storms, like from August 1st to 15th. Sometimes, some years that's an issue, and other years it's not an issue. But typically after August 15th, we really start getting into the peak of the season, and that really continues all the way through September. And so September is the correct answer for the most hurricane activity in the Atlantic. So this next graph, we're looking at annual Atlantic storm activities. So on the x-axis, you could see from May 1st through the end of December. The hurricane season is defined in the Atlantic from June 1st to November 30th. So in red is all the storm activity, so both hurricanes and tropical storms combined, and then the yellow is just the hurricanes. So you can see that typically, oftentimes hurricane season, you could maybe just have a very few couple of storms and not a ton of activity in the month of June and July. But then after August 15th, like I was mentioning before, the hurricane season really starts to ramp up. You could start getting multiple storms at once until it peaks during the first 2 weeks of September. And then hurricane activity starts to go downhill, but you can still get some very potent storms. In October, we've had, a number of Category 5 storms in the Caribbean and a number of hurricanes even making a U.S. landfall during the month of October. And then finally in November, activity starts to ramp down. And this graph is based on data from 1944 to 2020. So going through, looking at kind of the geography by month and then color-coded based on how active are certain areas. So in the month of June, on average, we get about one storm every year. Most June storms tend to either form sort of in the northwestern Caribbean Sea, in the Gulf, or kind of off the southeast coast of the US. So, we've had storms like Allison that flooded Houston in June and some other examples as well. In July, again, just a slight uptick in activity from June off the US East Coast is often where we've seen storms form and occur. The Gulf of Mexico is still fair game. Now, one interesting thing to notice is one of the exceptions to this was, if you remember, Beryl of 2024, it went right through the Caribbean, the straight moving Caribbean system in late June, early July. That was a pretty big exception. We would call Beryl climatological because there haven't been too many storms like it in the past. In August, activity really ramps up. On average, there's about 3 to 4 storms each year. The storms coming from Cape Verde, this is where the Cape Verde season really gets going, with tropical waves coming off of Africa forming. They can, go through the Caribbean, they can recurve out to sea, or they can come towards the United States, right? So it really just depends on how the steering is going at any given time with the Bermuda High and where these storms are going. And then September is the peak of the hurricane season. So really anywhere in the basin, it's possible to get hit. We have 4 to 5 storms every year on average. Cape Verde season is peaking during the early part of September. You can have long track hurricanes that, again, go towards the Gulf, Caribbean, or the US, or they could recurve. Now, one interesting thing about October is that typically in October, we have a little bit of a steering, of a change in the steering patterns. A lot of times we've seen in the past a lot of storms form in the Western Caribbean in October, but we don't have those systems coming all the way from Africa because really the Cape Verde season ends like kind of the end of September. So you don't have those tropical waves coming all the way from Africa typically, but typically you'll get formation closer in to the western part of the basin, which means that if there is a major hurricane or something that forms in the Caribbean, you might only have a few days to prepare for it before it reaches the United States. Now, Florida and areas in the southeastern US, it's much more likely that they would get hit compared to a state like Texas during the month of October. But we still have seen some further west in the Gulf. And then in November, finally, things start to quiet down, and you can still have some tropical storms or Category 1 and 2 hurricanes kind of reaching the US, but it's much more rare than in the earlier months. So the typical life cycle of a Cape Verde hurricane. Now, remember before I talked about that closed circulation. So this is just showing you a schematic of what often happens. A tropical wave will emerge off of Africa, and these red lines are representing the wind flow at the surface, like the streamlines of the wind flow. So because they're not making a circle, that means it's not a closed circulation. Like you just see kind of like this hill or backwards V. So that's the type of wind flow we have that are associated with tropical waves. However, if the system is able to attain a closed circulation and that more circular thunderstorm activity, that organized thunderstorm activity, then it's considered a tropical depression. And if the ocean waters are warm and conditions are favorable, it could strengthen into a tropical storm or a hurricane. Of course, sometimes these could make landfall in the US or they could move further south. But in this example, I want to show you the lifetime of one that undergoes extratropical transition, that is transitioning from a hurricane or a tropical storm into a extratropical or non-tropical storm. And a lot of times that happens when the hurricane starts moving over colder waters, when it gets farther north. Another way that can happen is when it merges with another extratropical area of low pressure or a frontal system, and then of course it will turn northeast and then eastward. And the reason why it will turn eastward is because in the mid-latitudes, those of you who live farther north, you know the wind blows from west to east. We have the mid-latitude westerlies. It's just the general circulation of how the winds work on our planet. But in the trade winds, in the tropics, you know the winds typically blow from east to west. That's why when the storms are further south, they typically will go from east to west. But once they get too far north, they're going to undergo the influence of those winds that are blowing it from west to east. And you can also see the cold front and the warm front on this once it becomes extratropical. So this is just an example of the lifetime of Hurricane Bill of 2009. You see that well-defined eye as Bill is making its way through the ocean, and it recurves and it's moving north. Oops, I meant to stop the video here. Oops, let's play that one more time. Because I just wanted to show you the difference between how it looks when it's a hurricane and when it's an extratropical cyclone. So this is still a hurricane right here. It's definitely still a hurricane right here because you can kind of see some semblance of an eye and still kind of a more compact. The darkest reds are those highest cloud tops kind of near the core of this hurricane. But then by the time it reaches the outer part of Newfoundland, a little bit further here, this is more of a extratropical structure. See, it's a little bit more. It has kind of a warm front extending eastward from it, and it's starting to develop perhaps a little cold front. And then it's all the thunderstorm activity is sheared off to one side. So by this point, it's undergone extratropical transition, and it's now fully extratropical. Okay, next question. Which of the following are ingredients for hurricane development? Do hurricanes need warm water, cold air, lots of moisture? Do they need strong winds aloft, or do they need icebergs? So I think there could be more than one correct answer for this question. So select all that apply. So we'll give you like 30 seconds or so.
All right, Andrew, answers are coming in. It looks like just about everybody's selecting warm water, and then another 2/3 are selecting lots of moisture. Maybe another third are selecting strong winds aloft.
Okay, yeah, so I'll explain that. So the correct answers are warm water and lots of moisture. So great job with that. And the reason why strong winds aloft is not correct is because that basically means that there's a lot of strong wind shear. Because what wind shear is, wind shear depends on it's how the winds change with height, how the wind direction and wind speed changes with height. And usually in the environment surrounding the hurricane, like outside the hurricane at the low levels, the winds are not very strong. So typically strong winds aloft during hurricane season in the tropics almost always is synonymous with strong wind shear. So so in this case, that one is not the best answer, but great job. And yeah, so continuing on that topic, ingredients for that are favorable for kind of tropical cyclone formation. A lot of times when we're explaining this, we talk about this. We use analogy for a vehicle, right? So one of the things is you need a pre-existing disturbance in order for a tropical cyclone to form, is basically what this is. And so an example of a pre-existing disturbance are those tropical waves that come off the coast of Africa, every few days during the hurricane season. Because those tropical waves have a little bit of rotation or spin with them, and they also have some usually initially disorganized thunderstorm activity. So that's one thing you need, and that can kind of be synonymous with like the frame of a car, because you have to have a frame of a car in order to have a car that drives. You also need to have a location several degrees north of the equator. And just the quick explanation for this is, so in the Atlantic, you won't see anything form between the equator and 7 degrees north latitude. And the reason for that is because there's 3 different sources of rotation in weather, and one of these is called Coriolis rotation. And the total rotation from these three sources is multiplied with each other, and Coriolis is 0 at the equator. So if you're multiplying 0 by other sources of rotation, zero times anything in math is 0. So that's basically the math explanation of why you can't get hurricanes to form near the equator, because it just won't allow you to develop enough rotation. Yes, so changing wind speed and direction with height, that is the vertical wind shear that I alluded to. If you're a hurricane and you want to strengthen, you don't want there to be a lot of vertical wind shear. You want there to be very low amounts of vertical wind shear, which means winds don't change very much with height. And yeah, so for the fuel, that is the warm water. So typically we're looking for water temperatures of 80 degrees Fahrenheit or above. But that will also, the exact number, whether it's 79, 80, 81, 82, that kind of depends on what the stability in the atmosphere. So stability in the atmosphere depends on the temperatures of the water, but it also depends on the temperature high up in the atmosphere, like at 30,000 feet. If you have a really warm water, but a really cold upper atmosphere, like up at the level where the planes are flying, then that means you have a really unstable atmosphere that allows the air to rise really quickly from evaporation and condensation, and then it allows thunderstorms to build and for the air to rise, which will continue to feed more thunderstorm growth, and it can lead to an area of low pressure forming. And it could also lead to just, that continuous buildup of thunderstorms that become better defined. And then finally, moisture is the other thing. Remember, I mentioned sometimes in June, July, and early August is when we most typically see those Saharan air outbreaks from Africa. But hurricanes need high relative humidity, especially between the surface and 15,000 feet, in order to form. So let's talk a little bit about these pre-existing disturbances, which was that number one on the 6 things that I just talked about. So tropical waves are one type of pre-existing disturbance, and they account for about 70% of all Atlantic Basin tropical cyclone formations, and for most of the major hurricanes. We have about 60 tropical waves emerging off of Africa every year, about one every 4 days or so, from May through September and into early October sometimes. And out of those 60, about 7 to 10 of them form into tropical storms. But we can also get systems that form, kind of farther west, not from tropical waves, that kind of decaying cold fronts. Sometimes, especially early in the season or even late in the season, you'll often see tropical storms form again, like in the Gulf or off the southeast U.S. coast, from areas of showers and storms that get left behind from the tail end of cold fronts. Maybe the front moves off, but you have an area of shower and storms that just continue to sit there, and then eventually they can get better organized. And finally, sometimes we see non-tropical lows and other thunderstorm complexes that sometimes they can become subtropical systems. But actually, one last year, I don't know if anyone remembers Hurricane Isaac from 2024 in the Atlantic, but that started as a non-tropical low, and then it actually became, I believe, a Category 2 hurricane, but it didn't affect land because it went eastward across the North Atlantic. So talking a little bit about track forecasting. So storm motion, track forecasting is it's controlled by large-scale weather features. The motion of where a hurricane or a tropical storm is going to move, it depends on other areas of high and low pressure that are in the area, like within several hundred miles or even within a couple thousand miles away, can affect the steering of these systems. So if storms don't move into high pressure, they typically follow the flow around areas of high pressure, kind of towards other areas of low pressure. So that that steering kind of makes it pretty straightforward. It's kind of like a cork in a stream. That's the analogy we use. Like if you throw a rock or a cork in a river, it's just going to move with the flow, right? Well, the atmosphere is a fluid as well. So if you have a hurricane that's in the atmosphere, it's just going to follow the direction that the atmosphere is moving the way the winds are pushing it. So numerical computer models forecast the track pretty well, especially, and I mean, track forecasting has been getting a lot better with every decade, especially every decade since the 1980s. There's been a big improvement in track forecasting. That doesn't mean we get it right every time, though. There's always a few cases where the track forecasts aren't quite as good as most other cases. But the reason for these improvements is because of the constant upgrading of model physics and of the resolution. And the reason we have better model resolution is because of that increase in computing power that we've had, that's pretty much continuous. As computers get stronger, it allows us to compute the equations of the atmosphere on smaller scales, finer resolution, and that leads to better forecasts. Now the intensity compared with track forecasting how strong the winds in the hurricane are going to get over the next few days is a little bit more challenging than compared to the track forecasting. And you know, it's a more complex problem because we have the factors of the environment, and we also have what's going on inside the core of the hurricane. So it's a multi-order problem that is not always so easy to forecast. The environmental factors are the first, third, and fourth bullets here. The upper ocean temperatures, well, you know, warmer water obviously is better for the storm, and vertical wind shear, if the shear is too strong, it's going to be weakening, and then moisture in the environment, right? And we already learned about those three things a few slides ago with the formation. But other things that affect the strength of storms is if they go over land, or especially if they go over an island like Hispaniola that has mountains over 10,000 feet, that can really significantly impact the intensity and cause a lot of weakening. And because when a hurricane goes over land, it loses its fuel source. Remember, the fuel source is the warm ocean. So if it spends too much time not over the warm ocean, it's going to weaken. And then you can also have things that are very difficult to predict, because even us hurricane specialists in the hurricane science community, we still don't fully understand the eye wall replacement cycles. There have definitely been increased efforts to try to predict these in advance during the last decade or so, but we're still learning about the structural changes in the inner core of the hurricane. You know, during those eye wall replacement cycles, you could have some weakening, and then you could have some re-strengthening on the time scales of 12 to 24 hours or so. And then finally, interactions with other weather systems. A lot of times, if there's another significant weather system, you know, within 500 to 700 miles of an approaching hurricane, it could adversely impact the storm, whether that other weather system is a tropical cyclone or maybe it's some sort of upper level trough. But there are also some cases where if there's an upper level trough exactly in the right spot, it actually may help a hurricane strengthen. So that's where the hurricane specialist's expertise on those upper level trough placements can help out with you know, predicting whether a system is going to strengthen or weaken. So I think this is either one or two slides left from my part. But there are different ways that we think about the size of hurricanes. One way that's depicted in this by the red circles is the radius of maximum wind. And that's basically like where the eye wall or the area of the band of strongest winds. Now, Charlie was a very small sized hurricane. It was a category 4 with winds of 145, I believe, miles per hour when it made landfall near Punta Gorda. But because the size was so small, I think it only had a peak storm surge of about 6 feet. Whereas when you get a really large storm, you know, you just get those wind impacts over a larger area, and you also get larger storms mean you could have a bigger storm surge too, but depending on other factors. But I'll let the storm surge specialist speak about that. But yeah, Wilma had an eye that basically covered you know, parts of these three, all the way from like Miami to West Palm Beach, had the eye wall with Wilma. So you know, there were millions of people inside its eye that had a lot of wind damage with that system. Oh, but the other thing about size I want to quickly mention is, besides the radius and maximum wind that you see in red, another way we measure size is by the extent of the tropical storm and hurricane force winds, right? Like, what's the radius of tropical storm force winds in each of the 4 quadrants? That's one of the things we have in our forecast products. We forecast that. out to 5 days. Right? We forecast the track, the wind speed, and the size. So if you don't know where to find that, I'm sure you'll be learning that within either today or tomorrow. And yeah, we also forecast how the 50-knot winds and also the hurricane force wind radius. How far out are they going to extend? Is it a big size storm or a small size storm? Right? Because Hurricane Sandy is one of the biggest storms in our database in terms of horizontal extent. So before we go to the next part, should we have time for if anyone has a question?
I think all the questions have been answered.
Oh, okay. You've answered all the questions in the chat. Very good.
All right, let's go to hazards.
All
Go to
right.
the next slide. All right, so thanks, Bags. You want to launch the question? Once again, I'm Larry from the Hurricane Center. And we're going through some hazards here. So first, before we get into hazards, just a knowledge check. What hazards has the greatest potential for the largest loss of life? Let's see, the questions are coming in here. Let's see, give you some time. Wind, rain-induced flooding, tornadoes, or storm surge. All right, so it looks like, we're over 400 responses. So about 60% of people said storm surge, and then 20% said rain-induced flooding, a little lower for tornadoes and wind. All right, so you're right. So this is just a pie chart looking at direct fatalities from tropical cyclones over the past 50 years or so. And then we also want to narrow it down to the last 10 years. So you can notice here that fatalities with tropical systems are really water related. You can see the past 50 years, storm surge and rain make up for about 70% or so, 70-80% of flooding fatality of water fatalities, where you can see that wind tornado is much lower. So water is really what kills people. But then we look at the last 10 years, you may say, well, storm surge has gone down. Well, we've had a lot of advancements in forecasting. We have storm surge specialist unit. We've helped criteria with evacuations and trying to critique those a little more with our forecast. So while storm surge fatalities have gone down over the past 10 years, it doesn't mean that that risk for the greatest potential loss of life still lies with storm surge. All it takes is, one horrible storm surge event, and this pie chart flips back to the one that looks like the one on the left. So the main takeaway here is really water is what kills people with tropical cyclones. So we've already learned the basics, climatology. So we're just going to assume hurricanes coming to your area. And we're going to step through all these hazards. And like I said, we have the storm surge unit here to really dive deep into that as well. So these are the main hazards associated with hurricanes: wind, waves and rip currents, tornadoes, storm surge, and inland flooding. As we're kind of going through these hazards, just think about where you are in your area. If you're more inland, you don't have to worry about storm surge. What kind of hazard do you really have to focus on for your community? Is there a vulnerability area? Is there topography that you have to worry about where wind may become an increased hazard, say inland, it's a perfect example with Helene, or inland flooding. So as we go through these hazards, try to apply them to you locally in your community and how you would deal with them, or maybe you're unfortunate you have to deal with all of them at once. So we'll start with wind here. The Saffir-Simpson wind scale. Hopefully you're all fairly familiar with it, and it goes from tropical storm once we get to that 39 mile per hour threshold, and it goes all the way up to a category 5. You can see a few examples here. In the past few years, once we get to the major hurricanes, really we start to see that devastating, damaging, life-threatening impacts. But this is really only estimating wind. And as you saw in the previous slide, wind is just one of the hazards that is associated with these storms. You don't see anything in these categories about storm surge, inland flooding, or tornadoes. So, when we say that the category, it's a category 1 system, it's only talking about wind. So you need to really account into those other factors, what impacts and hazards you could have in your local community. And the category or the tropical storm is really only tied to the wind. Doesn't take into account all those other hazards that come with tropical cyclones. So we'll step through the wind hazards here first, just to go through what each of these categories, what kind of damage they bring. So as we go into the category 1 threshold, so anything from 74 to 95 miles per hour, it's going to be a category 1 hurricane. What kind of damage does that produce? Some damage, trees down, well-constructed homes, could have some roof damage, large tree branches snapped, falling into power lines and poles, and your outages and power and potential water could last several days with a category 1 landfall impacting your community. We step it up a category to category 2. What does that look like? You're going to take that damage threshold and you're going to have extensive damage now. Well-constructed homes sustain major roof damage. Many of the shallow-rooted trees are basically snapped or uprooted and completely gone. And you have near total power loss to your entire community that could last for several days. If it's impacting a community of high rises, you'd have windows blown out from the high winds from the system making landfall with skyscrapers and big cities. So how does this impact the local area that you serve? Then we're going to step up to category 3. So we're going to go into major hurricanes. That's where we get that devastating damage where homes basically are major damage or no longer livable. Basically, all the trees are snapped or uprooted within an area. Electricity and water may be unavailable instead of just several days. Maybe we're talking potentially weeks now with a major hurricane with wind damage in your local community. Category 4 is really starting to get that catastrophic damage. You see some of the examples here from Charlie and Punta Gorda, Maria, which hit Puerto Rico. That's actually a picture of what was left of the weather radar. You see the whole top is completely blown off. Or Laura in Louisiana, just nothing there. Constructed homes are sustained damage or gone. All trees are basically snapped and power poles are down. And now our time frame is not days anymore, it's weeks to potentially months that you can be without power with the category 4. Category 5, these is bad as it gets, greater than 156 miles per hour. Unfortunately, we've had a few of these in Florida, but there's an example there of Michael, all trees snapped in half, and Andrew down in South Dade, basically all homes completely destroyed, and basically your residential areas are completely isolated, and power outages once again on that time frame of weeks to potentially months. So let's talk about a little more about these category 5 landfalls, and where were they 5 days out. So we have Labor Day 1935, Camille 69, Andrew 92, and then Michael 2018. Where were these 5 days out on the map on the right? And you say, no, my slide's not glitching. They were not there. They were not hurricanes 5 days before landfall. So think about your timelines. 5 days out, you're usually starting to make plans. But category 5, 5 days out, they were not hurricanes 5 days before landfall. Let's see, 3 days out, where were these hurricanes 3 days before? So the Labor Day hurricane was a 40-mile-per-hour tropical storm east of the Bahamas. Camille was south of Cuba as a 65-mile-per-hour tropical storm, still not a hurricane. And then Andrew was also a tropical storm, 50 miles per hour winds 3 days out. And Michael was also a tropical storm 3 days out, moving through the Yucatan Channel. So even 3 days out, these systems were not hurricanes before landfall. So that's kind of the wind. We're going to move into the storm surge hazards now. I'll pass it to Heather Nepal, the storm surge specialist, to kind of walk you through the hazards that are associated with storm surge.
All right. Good afternoon again. My name is Heather Nepal. So as Larry mentioned, historically speaking, storm surge has the potential to result in the largest loss of life. So it's kind of the reason why we have a specialist unit dedicated and devoted to the storm surge forecast. But I just want to show you here what I have is the 3 of the top 5 hurricanes that have caused the largest either loss of life from storm surge in recent years, as well as the costliest. So of course, Hurricane Katrina still holds the #1 spot for the costliest hurricane on record thus far, with 520 direct deaths, largely many of those due to storm surge, unfortunately. Hurricane Ian has crept up to the #3 spot in 2022 with 66 deaths resulted from storm surge. And then Hurricane Sandy in 2012 still holds the #5 spot with 72 deaths. So when we think of storm surge, though, we kind of think of it as kind of this all-encompassing part of the hazard itself, but storm surge itself has a very specific definition, and that is it's the abnormal rise of water that's generated by a storm over and above the predicted astronomical tide. So we have here this little schematic on the right. You can see it's an unfortunate time for this area of the coastline, but we have a mean sea level, right? And then we have 2 feet of normal high tide depicted there. And so what that normal 2 feet of high tide is, it's just a normal rise of water level every single day at this coast at high tide. So the water comes in, raises to 2 feet at high tide. And unfortunately, we have a storm that's impacting this. And so what that storm is producing is 15 feet. And so that 15 feet is of water that's being produced by the storm over and above that astronomical tide of 2 feet. But we can combine those two and we get a separate definition called storm tide. And that's just the water level due to the combination of the storm surge and the astronomical tide. So we can add the 2 feet of normal high tide that occurs every single day along the coast on top of the 15 feet of storm surge that this storm is producing. And then we would get 17 feet of storm tide right along the coast there. But we do, even though storm surge does have its specific definition, social sciences have told us people tend to take action with the word storm surge. So just keep in mind that when we do mention storm surge, we are including the tide, even though it's not part of the official definition. But you'll see here we have a third definition on the screen, and that's inundation. And you'll see that a lot in a lot of our discussions and products. And inundation is just basically that's flooding on ground that is normally dry as a result of the storm tide and other possible factors. So where you see that house on any given day is not flooded by the 2 feet of high tide. So that house, unfortunately, at this schematic is being inundated by maybe, say, 2 feet of water that's above normally dry ground. So those are some definitions that you might hear. And so here's a really good example that we like to show you guys as emergency managers. This was taken in Waveland, Mississippi, prior to Hurricane Katrina. And so you can just see this nice, cute little quaint house, nice mowed grass. If you keep an eye on that tree, though, this image was taken prior to Hurricane Katrina, and then this was taken after. And so you can see what a very deadly and dangerous situation this could be if someone were to stick around. Because not only can people lose their homes, they can potentially lose their lives as well. And this is another really great example of why we evacuate people, why we don't want people sticking around for this kind of phenomenon. And here's another really good example from Hurricane Ian back in 2022. So this is from a YouTube video, but these are just still shots. So this image was taken, stopped at 10:38 a.m. You can see the surge is starting to creep into the roadways there. Keep in mind, in that house, there actually were 2 people that we were aware of that we found out later on. If we fast forward from 10 to just 4 hours ahead, we can see what a very different situation this is. So now the water levels are increasingly higher. You can see there's debris flowing through that water. If I fast forward another hour, that house is no longer on the foundation. As I mentioned, there were originally 2 people in that house. Thankfully, they did get out, they did survive, but imagine how scary that situation and how deadly and quickly the situation has become for them in just 5 hours, by the way. If I fast forward another hour, we can see that now the water level is, basically almost overtopping the camera, which I believe is about 12 feet above the ground here. So you can see not only is the water level now, incredibly high, but we can see additional wave action that's accompanying the surge, which is making the situation even more dangerous. And if I fast forward just 2 hours later, we can see the water levels dropping, and now the water level is starting to recede. So you can just see how quickly this situation can become very dangerous. This is, 6 to 7 hours from the start of the event to now the event starting to recede. And basically, there's not really much that's going to be left here, as you can imagine. So again, this is the hazard that we evacuate for. We don't want people sticking around for this. And unfortunately, if you have a coastline, you are vulnerable to storm surge. Certainly, there are areas that have been impacted more frequently or more recently than other areas along the coast. But if you have a coastline, you should be preparing and understanding your risk to storm surge. So before I get into some of the factors that affect how much surge a particular storm is going to produce, I kind of want to go quickly through a storm surge history along coastal regions. So we'll start with the Gulf Coast, which has had its fair share of storms recently. You'll see Hurricane Zeta, Laura, and Hurricane Hannah all impacting the Gulf Coast and along in 2020. So we see Hurricane Zeta here impacting the Biloxi, Mississippi area. Hurricane Laura, unfortunately, devastated Cameron Parish, Louisiana. We can see the image there on the top right. That's actually water levels that hadn't receded, that was taken several days post-storm. But we can see the water levels are still lingering. Hurricane Hannah, as I mentioned, also in 2020 impacted the Corpus Christi area in Texas. And then Hurricane Michael in 2018 impacting Mexico Beach, Florida. We can see a lot of those homes being lifted off the foundation, likely due to the accompanying wave action that accompanied the surge as it moved inland. Moving up along the coast, we have the southeast. So Hurricane Isaias also in 2020 impacting Oak Island, North Carolina. You can see the sand deposit that was left behind from the surge in that image there. On the top right is Hurricane Hugo, which is a very infamous storm for Garden City Beach, South Carolina, impacted that area in 1989. We had Hurricane Matthew in 2016 impacting Tybee Island, Georgia. And then interestingly, in 2017, we had Hurricane Irma. And you can see here, this image was taken in downtown Jacksonville. And if you have any idea of that, if you have any recollection of that storm, or if you have any idea of how the topography or geography of Florida is, Irma actually made landfall in the far southwest corner of the peninsula down in Marco Island. And Jacksonville is about 340 miles to the northeast of that. And we can see there's pretty significant storm surge flooding in downtown Jacksonville, even that far away. So you don't have to necessarily be near the center of the landfall point to get significant storm surge. So keep that in mind. We'll kind of talk about what that is in just a moment. Moving up along the coast, we have the mid-Atlantic. So Hurricane Isabel, pretty infamous in 2003, impacting not only Baltimore, Maryland, but also the Hampton Roads, Virginia area. And then we have Hurricane Sandy in 2012, impacting Brick, New Jersey, as well as Staten Island, New York there. And then last but not least is the New England coastline. So again, maybe hadn't had any more recent storms, but again, still very vulnerable to the potential impacts of storm surge were they to have a storm make landfall. So here's some pretty significant storms from that region. So we have Hurricane Carol in 1954 impacting the Groton, Connecticut area, Hurricane Irene in 2011, Hurricane Sandy also making an impact in Montauk, Rhode Island. Again, likely those houses being lifted off the foundation due to the accompanying wave action with the surge. And then last but not least is the 1938 hurricane, which you can see produced some pretty significant storm surge flooding in Providence, Rhode Island. So when we think about, our mental model of a hurricane, if I were to have a poll up, and ask you, where does storm surge occur? I would probably assume most of you would say the right side of the storm, right? Typically, our mental model tells us the right side of the storm is the hazardous or the dirty side of the storm. And in this case, that's true. So this is an image taken from Hurricane Sally. And we did have pretty significant storm surge impacts from the right side of the storm. Of course, the maximum of that storm surge likely right near the landfall point. But we did have large amounts of significant storm surge flooding, even all the way out into the Apalachicola area, the Big Bend of Florida. So again, pretty significant widespread swath of life-threatening storm surge there. And on the backside, typically we can get winds that push the water out back to sea. And a lot of times we can get kind of what we call a negative surge, where the water pushes so far out to sea that it eventually can expose the bottom of the bay. So this happened in Hurricane Sally in Mobile Bay, where the winds were able to push the water out to shore. Also happened, I believe, in Hurricane Irma in the Tampa Bay area. So for a period of time, the bay was completely exposed, but only temporary, because you can see how quickly the water can move in and out of that area. So, but this is a case where, you know, that mental model of right side of the storm is the dirty side, the left side is the less hazardous side. This is where we can see this break down a lot, especially when it comes to storm surge, because if you look on the back side of the storm, we have this southwest Louisiana coastline, which if you're just looking basically on the left side of the storm, you might think, oh, well, they're safe. But really, plain and simple, water goes where the wind pushes it. And in this case, when we did have winds pushing water onto that portion of southeast Louisiana coastline. So we can get storm surge flooding even along that area. So those are things to be thinking about. If you don't remember anything from my portion of the talk, please do remember water goes where the wind pushes it. So but there are other important factors. So I do have a poll here to ask you what you think are the important factors in determining how much surge could occur from a storm. So you have A, size of the storm, B, forward speed of the storm, C, intensity, or D, all of the above. And looking at some of the results so far, I'll give it a few more minutes. What happened there?
We lost your presentation.
I'm not sure what happened. Are you able to reshare your screen on your end?
Yeah.
Escape.
Maybe we lost.
Yeah. Try.
1 second, folks. Technical difficulties. Apologies.
Share your screen.
I see it.
Is it good full screen?
Yep.
All right, sorry about that, guys. I don't know what happened. I could see everything just fine. So yes, the correct answer is D, all of the above. But there are various amount of factors that go into determining how much surge a particular storm is going to produce. So as you can see, I have them all listed here. And we're going to go through each of these individually to show you how each of these can individually impact how much surge just by changing each of these factors can influence the surge. But really think about it's all of these combined holistically that will really determine how much surge a particular storm can produce. Keep in mind, certainly not all category 4s are going to produce the same amount of storm surge. It's really all the combination of these factors. So first off and foremost, yes, intensity. Stronger storms tend to produce more storm surge. Storm size is what we denote by the radius of maximum wind. So that's the radius of the eye wall where the winds are the highest. So larger storms, so where you have a larger eye, tend to have larger storms, and larger storms tend to produce more storm surge. Forward speed, so how fast those storms are moving, are going to impact how far inland that water is going to penetrate. So slower storms tend to have a further inland extent of storm surge. Angle of approach is really going to alter the focus of where those winds are going to be pushing that water on shore. And then last but not least is that width and slope of the shelf. So the bathymetry of the coastline is really going to be the determination of the vulnerability of your coastline. And so more gradual sloping shelves tend to have more storm surge. So again, I'm going to go through individually an example of each of these. So we'll start off with intensity. So here we have a Category 3, just an arbitrary Category 3 storm moving to the northeast, making landfall near Sarasota. And we can see that just based off of this single storm characteristics, we can see there's pretty significant flooding in this Fort Myers, Port Charlotte area. And if I just simply increase the intensity, I keep the storm size, the angle of approach, I keep the forward speed all the same, and I just increase the intensity from a Category 3 to a Category 4 storm, and I'll toggle it for you. So here's the Category 3 and Category 4. Here's the 3 again, and Category 4. So just simply by increasing the intensity, we can see not only are those maximum values of surge larger along the coast, so you see a lot more of the red, the greater than 9 feet of storm surge above ground. But you also see a little bit further inland extent of that storm surge flooding footprint just by simply increasing the intensity. Next is the size of the storm. So remember that radius of maximum wind. So kind of the size of the eye is going to denote the size of the storm. So that circle here. So this is a storm making landfall along the Georgia coastline. This circle here is just denotes the size of the eye wall of this storm. And so you can see that again, based off of this one single storm, would be the flooding footprint based off of this storm. So again, I'm going to iterate now through a few images as just showing you as the storm gets larger, keeping intensity the same, keeping forward speed, keeping the track all the same. I'm only going to be increasing the size of the storm. We can see how that flooding footprint changes just by changing the size of the storm. So here's a larger storm and another larger storm. We can see that again, not only is the maximum amount of surge, those greater than 9 feet of storm surge, increasing along the coast, but also the inland extent is also increasing as we increase the size. So this kind of makes sense, right? So you have, if you're splish splashing in the beach or at the pool and you're trying to push water, it's a lot harder to push water with your hand as opposed to your entire arm. So sort of kind of same concept here with storms. So larger storms have the ability to just push more water than say smaller storms. And so here's another image. So the next is the effect of the forward speed. So again, how fast that storm is moving. Here I have a storm moving northwest at 25 miles an hour, making landfall along the Louisiana coast. Again, we can see just the flooding footprint based off of that single track storm. And again, if I just slow the storm down, I keep intensity the same, I keep storm size the same, keep track the same. I just slow the storm down from 25 miles per hour to now 5 miles per hour. We can see how different that flooding footprint is. So again, I'm going to toggle it. So here we have a storm moving 25 miles an hour, and this is your slower 5 mile per hour storm, the 25 mile per hour, and then the 5 mile per hour. We can see that faster storms tend to produce a higher maximum of storm surge right along the coastline compared to slower storms, which have a much further inland extent of the storm surge flooding footprint. And again, slower storms, that just means that the storm has more time to push water. And that water has to go somewhere, so that just means it moves further inland. So that's how forward speed can affect how much surge the storm can produce. Next is angle of approach. So here we have a storm moving north-northwest, making landfall along the New Jersey coastline. We could see that from this storm, we can see there's pretty significant flooding here in the Raritan Bay area, the backwaters of New Jersey here, along the south shore of Long Island. And again, if I just simply tweak the track, right, I keep the intensity the same, I keep the storm size, the forward speed, I'll even make landfall in the exact same location, right? If I just simply tweak the angle of approach from north-northwest to west-northwest, again, I'll toggle it so you can see the difference, right? But just by simply tweaking that angle of approach just ever so slightly, we can see that the flooding footprint is significantly different here along the Raritan Bay area, even these backwaters of New Jersey, and then again along the South Shore of Long Island, if I just continue to toggle it. And so what makes this angle of approach a little different is that this more west-northwestward motion allows water to, the winds to really funnel that water and push water into the Raritan Bay. And bays tend to act as kind of like a catcher's mitt, allowing the water to pool in there. So this is the reason why Sandy was so deadly in terms of storm surge, because the angle of approach was just right to really funnel the strong winds into the Bay Area. So again, water goes where the wind pushes it, right? So if the angle is just right, you can have pretty devastating effects along the portions of the coastline, especially in those more vulnerable areas. Which, speaking of vulnerability, is again the width and slope of the shelf. So on the left-hand side, we have a wide, gentle sloping shelf, very similar to what we see along the Gulf Coast region. Compared to the right-hand side, which is a more narrower, sharper sloping shelf. And we can just see the difference, right, in terms of storm surge impact. So these wider, more gentler sloping shelves doesn't really need a lot of energy for the water to really just bulldoze itself onto shore, compared to these narrower, sharper sloping shelves where it's really the wave action that provides the energy in terms of pulling, I'm sorry. Okay, sorry, I thought I heard something, but let's see if I can play this again. So the narrower, sharper sloping shelves, it's the wave action that really provides the energy for the water to move up and onto land. So again, not to say that if you live along the coast with a narrower shelf line doesn't mean you're immune to storm surge impacts. Absolutely not. You still have a vulnerability to storm surge. It just may not be to larger amounts to storm surge as compared to the wider, gentler sloping shelves. And so here's a really good example of that. So here we have the bathymetry off the southeast coast of Florida. So Palm Beach County, Broward County, and even portions of Miami-Dade County here along the southeast kind of reside along this narrower, sharper sloping shelf compared to areas in Dade, which touch the Biscayne Bay Area, which is a lot more shallower and gentle sloping. So here's a really good example. So I have a storm moving due west and just an arbitrary coastline, and it's probably hard to see, but if you squint really well, there is some storm surge flooding just right along the barrier islands, but not so much further inland. And again, that's just a function of the bathymetry of the coastline. But if I were to just shift that storm south, keeping all of those other factors the same, keeping the intensity, the storm speed, storm size, all the same, and I just shift that track from Palm Beach now to Miami-Dade, we can see how the flooding footprint changes. This part of the Florida Peninsula here is very much more vulnerable to storm surge, just simply due to the bathymetry of Biscayne Bay there. So really important. It's all really about location, right? So here's what we have, what we call a Category 4 MOM. So you'll learn about those tomorrow and how those are calculated and created, but basically what you're looking at is for any given Category 4 storm, you'll see the maximum amount of storm surge along the coastline for that category. And so certainly just by looking at this map, there are areas along the coast that, really stick out in terms of vulnerability. Of course, a lot of areas in the Gulf Coast, like Louisiana, the Big Bend area of Florida is very vulnerable to surge. And again, this is all due to the fact that those reside in a much more wider, gentler sloping shelf compared to, say, again, the southeast coast of Florida, and even the Outer Banks of North Carolina, much less vulnerable to storm surge than those other areas that I pointed out. And so as I mentioned earlier in the Hurricane Ian images, there's wave action that's also accompanying the surge. And the wave action can also result in a very localized rise of water level right along the coast as a result of the breaking wave action. So we can see here, when you think about the waves at the beach, right, the waves crash on the shore, the water runs up, and then the water runs back down typically, right? But what happens when you have a storm making landfall, not only are those waves bigger crashing along the shore, but they're crashing a lot more frequently. So the original water that was able to crash, run up the shore, now doesn't have a chance to run back down out to sea before subsequent waves crash. And so what happens is we get this really this phenomenon called wave setup, which is again a very localized rise of water right along the coast as a result of that wave action on top of the storm surge that the storm itself is producing. And if you haven't figured it out, it's really a total water level problem, right? At the beginning, I said astronomical tides. Tides are just a natural rise of water at the coast every single day. On top, and then you have storm surge that can account for that total water. And then now that wave setup, which is again that localized rise of water at the immediate coast as a result of the wave action. And then there's, as you can see, a fourth component to the total water level rise that I haven't even talked about, and that's fresh water. So that's water that's fallen at the coast, that's rain, or it's fresh water from a river that meets up with the ocean. However, here at the Storm Surge Unit, we are only able to account for the first three components, so the storm surge, the astronomical tides, and the wave setup. You'll hear from Larry and about who can provide the freshwater input next. But with that, I will segue back to Larry to talk about the rest of the hazards.
All right. So let's talk about more some of the other hazards. We're going to get into some more of the other water hazards, as the chart here that I showed earlier shows about 9 in 10 deaths with tropical cyclones do occur due to water. So let's get into this kind of the freshwater flooding. Really, the past 10 years, and even you've noticed the chart on the right doesn't include Helene either. So that rainfall flooding death total maybe even a little higher once we include 2024. But just take a look here at some of the flash flooding, inland flooding, river flooding, and the impact that it can have in your area. We look at a few examples here. This is Tropical Storm Allison. This is a view of I-10 when Allison moved in, and what I-10 looked like after Allison dumped a tremendous amount of rainfall with flooding basically covering the entire highway. You can see multiple vehicles submerged, or even just floating down the highway. You see all the trucks stacked up there as well. Another example in Texas is Harvey. The image on the left is the normal day, but after Harvey moved through, on the right there, you can see the water is basically up to the street sign. So just the amount of water funneled down, sitting on the roadways, and just pretty much stagnant there with Hurricane Harvey in Houston. Just another example in the downtown metro area. You can see how everything kind of funnels down into those valleys or where the streets lie. So the image on the left is before Harvey, and the image on the right, you can even see that lower area is completely flooded with water completely down that street, and covering much of the buildings there as well. So just an example of the magnitude volume of water and what that can look like. So that's kind of more volume, a lot of water sitting on a highway, just kind of still, slow moving. But there's the other side of it too. When we get terrain and topography with a tropical system, it's not all about the magnitude or amounts of water. It's also the speed. So if we have water that falls and begins to move downhill, down topography, that rapid movement of that water can cause damage as well. You see this a lot in the Appalachians when we get rainfall moving into that part of the area, or some of the islands, Puerto Rico. When the water falls, it flows downhill and it's very quick moving and causes damage, can lift houses off their foundations and cause damage that way. And just another example of where, terrain and hilly topography causes water to rush downstream and cause damage too. So with inland flooding, there's just the massive amounts that completely flood roadways and shut down cities and urban. But then in the rural areas, doesn't always have to be those high values. It could be some rain falling at higher elevations, and then it begins to flow with that speed of that water moving downhill that can cause some of the damage as well. So it's really important to know your local area, and it doesn't have to be 60 inches like Harvey. It could be 5 to 10 inches in topography with that fast motion of water that can cause a lot of damage, taking houses off their foundation. So what kind of factors go into, rainfall, the amount of rainfall with a system? It's pretty complex. It really goes into the actual storm, and then also where's the system going? So for forward speed, a slower storm means it sits over the same area for a longer period of time. A perfect example is Harvey. It was moving fairly slowly, and you get more rainfall. The size of the storm, a large storm is going to produce more rainfall. It's going to rain for a longer amount of time due to the size. So that one, pretty common sense there. Topography, we saw a lot of this with Helene, unfortunately, this year in the Western Carolinas. More rain on the windward side of the mountain. So where that wind is blowing, you get more heavy rainfall on that side, and topography, how that can eventually lead to those water flowing downhill and the speed of the water causing damage as well. As tropical systems interact with fronts, moving across the Central Plains, you get enhanced rainfall. Really, Mid-Atlantic is another perfect example of that, where the system moves inland through the New Orleans Gulf states and interacts with other weather systems. You get all this tropical moisture moving inland and combining with either a colder air mass with a cold front moving through, and just amplifies those rainfall totals. And then the storm track. We've all seen 4 asymmetric storms. Say the right side of the system is the one that has all the rain. So if the storm comes in to the right of you, you may see less rainfall just to the nature of the storm and where the storm actually goes. It can alter that focus of rainfall over a local area. So here's an example of Tropical Storm Alberto in 2006. So you can see the track of Alberto is there. It's interacting with a cooler landmass coming off the Appalachians. You get all this warm tropical air moving in and combining with this cooler front. Air begins to rise, and you get a very heavy area of heavy rainfall. So it's a combination of not just the system of Alberto, but also interacting with this cooler air mass flowing off the mountains, interacting with this very moist atmosphere, and you get a large area of heavy rainfall occurring where that interaction occurs. So this is what the rainfall totals for Tropical Storm Alberto looked like. So just to focus there, a wide swath of 4 to 7 inches across the area. But you see how tight that gradient was. It was really where that combination, where that collision occurred. If you move a little bit further east or a little bit further west, those gradients significantly drop off. So it's really, imperative, where does that collision occur? That's where the heaviest rainfall will happen. Another example in the Carolinas, sorry to pick on the Carolinas if you're from there, Hurricane Florence in 2018. This is just showing the forecast from the Weather Prediction Center on the left-hand side. You can see, if you compare to what actually happened on the right, it looks pretty similar. The colors are all there, but it makes it a little smoothed out on the left-hand side, but it just goes to show the little subsequent geographic features, or a heavy rain band moving in can help delineate where that heaviest rainfall occurs. But overall, the big picture on the left 5 days prior to what actually happened there on the right looks pretty good, but there are some finer details of geographic, or where did that strongest rain band come ashore, and you can kind of see that in the stratification there on the right, where some areas got 3 feet of heavy rainfall in North Carolina. This one we always like to show is Tropical Storm Cindy in 2017, how rainfall can vary over a very short distance. So we're talking about 7 miles here across, and you can see To the left, they had a very strong rain band come through, and you had about a foot of rain. And then 7 miles to the east, you were outside of that rain band and you only had 3.5 inches. So it really does depend on where these smaller features do set up to how much rainfall you could get for a given location. And it's just the granularity of tropical systems and how their rainfall is produced. Another example of a low in 2016 in Louisiana, you can see a large area of heavy rainfall that occurred well inland. You're talking areas greater than 10 inches of a large portion of Louisiana, with some areas in Baton Rouge experiencing over 20 inches of rainfall. So just goes to show, rainfall can be very large, widespreading, like this particular case, or it can be very granular where, you go 7 miles and you're talking about a difference of, 7-8 inches of rainfall, and what those impacts can do to your local community if you're just 7 miles to the left or 7 miles to the right when it comes to heavy rainfall. Another hazard with hurricanes that probably don't get talked about as much, but is tornadoes. This past year, Hurricane Beryl, Milton come to mind, producing tornadoes. Landfalling hurricanes produce about 70% of them produce at least one tornado, and 40% produce more than 3. But we can have tornado outbreaks occur, and the perfect example is Hurricane Ivan, as it made landfall in the Gulf and then continued to move northward, produced 117 tornadoes throughout the entire span as it continued to move well inland. And if I go back, so this is the day of landfall on the 15th, we had 29 tornadoes. As it continued further inland up the eastern seaboard into Georgia and the western Carolinas, you had 23. Once we reached the mid-Atlantic, so we're talking 2-3 days after landfall now, we're still having impacts from Ivan well into the mid-Atlantic, where we had almost 60 tornadoes that occurred there. So this is a perfect example of, the storm is making landfall in the Gulf. I'm in the mid-Atlantic. I don't really have to worry about it. Hurricanes have multiple hazards. You may not be dealing with the devastating impacts of a landfalling hurricane, but you may be dealing with the aftermath of whether it's rainfall or tornadoes moving into the mid-Atlantic. And Ivan is a perfect example. A few days after landfall, the mid-Atlantic has a tornado outbreak where you may not have been paying attention if, Ivan's down the Gulf Coast. So hurricanes come with many different hazards. So it's always, you got to pay attention to all of them. Where do tornadoes form usually during hurricanes? They usually occur in that right front quadrant. You may have heard the dirty side of the storm. It's on the right side, the way the spiral rain bands move inland over land in that right front quadrant, you get some friction over land, which creates favorable conditions for these storms or cells in those outer bands to begin to start spinning. And they can occur well away from the storm. You can talk hundreds of miles from the center of the system. You could have an outer rain band that is producing tornadoes, and this tornado potential can occur well after landfall. Like I said, it could be days after landfall where we get tornadoes from hurricanes. Usually, tornadoes that happen in hurricanes are usually on the weaker, short-lived end, but they can be pretty intense. Milton had a few EF2, maybe even EF3 tornadoes down here in Florida. So while on average they're usually smaller, short-lived, a little bit weaker, you can have some large, strong tornadoes with hurricanes. And the final hazard we'll touch on, and it's really one that's becoming more prominent in the past few years, is waves and rip currents. Another part of that water hazard that kills people. Swells from large hurricanes, wave action, and wave energy can impact the entire areas of coast, whether it's in the Gulf or the entire Atlantic basin, from a storm that can remain well offshore. An example, in 2019, Hurricane Lorenzo moved well offshore, but we had 8 people die due to drownings of rip currents and hazardous surf at the beach. What was a nice beach day, they weren't taking into account the hazard that was actually from a distant hurricane, and they got caught in rip currents and drowned. And this can happen in the Gulf of Mexico as well. We had 2 people die in Florida in Hurricane Delta. Didn't have any other impact from the storm, no rain or any other impacts, but they went to the beach that day and were not aware of the wave energy and the rip currents that were being produced. And 2 people drowned there as well. So even though these storms, they're out to sea, no big deal. If you're a coastal community or involved with beaches and the safety there, it's something to keep an eye on, because even though the storm may pass hundreds or even thousands of miles offshore, that wave energy can make it to the coast. And unfortunately, we've seen fatalities due to rip currents increasing from these distant hurricanes, just because it's a nice day at the beach, but the water is not somewhere where you want to go. So just another hazard that we kind of don't think about if we're not being impacted, but it's becoming an issue where we've seen some fatalities, especially in the last few years, increase as well, which kind of contributes to that, 9 in 10 people die due to water hazards and tropical cyclones. It's that water that's really killing people, with whether it's the waves and rip currents, the inland flooding, or the storm surge. So with that, I don't know if we have any more questions unanswered. Zane, I'll pass it to you to hand off. I think we're gonna go to a break, but if you wanted to say any comments or any questions on Unit 1.
Hey, thank you, Larry. No questions right now in the chat. And thank you, everybody that is posting those questions. Please let us know if anything else comes up, both with the material that we have or any of the resources that have been identified. We're doing our best to answer those questions quickly and succinctly. I just want to say thank you to the National Hurricane Center team. Great kickoff to the course. We'll take a 10-minute break here, so if we can get you back by 2:50, that would be great. Pending anything else from the panelists or from the presenters, we'll see you at 2:50. Thanks all.
Well, let's get started. Welcome back. So the first unit, we covered the basics of hurricanes, the life cycle, and most importantly, the hazards, because as emergency managers, that's what we're actually going to be responding to. So now we're going to talk about where you get your information. Again, my name is Matthew Green. I'm one of the 2 FEMA liaisons here at the National Hurricane Center.
And I'm Michael Spagnuolo, working alongside Matthew here at NHC, supporting FEMA as the liaison. I was previously with the state of Florida at the Florida Division of Emergency Management. I am also a firefighter EMT.
Okay, excellent. So in Unit 2, what we're going to do is, by the end of it, you should be able to speak to the NHC text and graphical products, explain those products when they're available, and be able to explain where you would find the critical information that is in the products to answer some key questions. So what we're going to do today is we're going to talk about how, the Hurricane Center is going to be providing you the big picture, the 50,000-foot view. And that's actually what's going to complement and guide the local forecast office products. So we're going to walk through all of those products, but it's important to sort of understand that when we're many days out, we're going to have fewer products with more uncertainty. And as we get closer and closer to the actual incident, we're going to get more and more information, more detailed information. And by the time we get to the actual warnings and the actual impacts, we're going to have a constant flow of information that's going to guide you to understanding the threat.
So Matthew and I have this unit set up to cover some of the frequently asked questions that Matthew and I get in our support for emergency managers. And I'm sure many of you, as probably the de facto hurricane contacts for your agency, receive very similar questions. So we'll start with the routine product that is issued throughout the season, kind of as that go-to at the start of the day when the first threats are developing, because you want to answer the questions for what's going on in the tropics, and what areas have that potential for a new system to develop. And that product is the Tropical Weather Outlook. Tropical Weather Outlook is issued throughout hurricane season, actually starts a little early before the Atlantic season on May 15th. 4 times a day, the Hurricane Center will issue this product, regardless if there's a threat of development or not. They will issue this product at 2 a.m., 8 a.m., 2 p.m., and 8 p.m. Eastern Time, so 1 and 7 for Central Time. So throughout the season, they'll provide this product. They can issue a special outlook in between those times should there be a significant or unexpected change. You'll hear us reference special tropical outlooks or special advisories a few other times in this unit. while the Hurricane Center follows a pretty regular schedule for providing their forecast products, they're also not going to just sit on information for 4 or 5 hours if something is changing just to wait until they get to their standard issuing times. They will go ahead and if something's changing at 4 p.m. in the afternoon, they will let you know and provide a special outlook. But by default, they will have this product 4 times a day. Now, the Tropical Weather Outlook has a text component and a graphical component to it. We'll start first with the text product. Of course, that's where it's going to give you the actual details. Each area of interest that is across the Atlantic basin that they are monitoring for potential development into a tropical cyclone, they will have a geographical header, and that'll kind of be like your reference point. And then there'll be a few sentences written by the forecaster talking about where the system is, where is it going to be going, what's the potential for development, maybe some of the factors that are either supporting it or hindering its development. And then, of course, where is it going to be heading over the next couple to several days. Maybe they've got Air Force or NOAA Hurricane Hunter reconnaissance scheduled to go fly the disturbance to give it an investigation. And then they have a timeline for maybe when they're going to consider issuing watches, or if they're considering a potential tropical cyclone, they can have information in here as well. And then they wrap that up with a chances for development. They assign it a percentage chance from 0 to 100 in intervals of 10. And that percentage correlates to a category low, medium, or high. They provide those chances of development in both the 48-hour timeline, so over the next 2 days in that short-term development, and then they provide a 7-day or that week-long development chance for that system. Now, you're probably even more familiar with seeing this in graphical format. This is the graphic for the 2-day development chances. You see X's that mark the current disturbances that are on the map, and then the associated percentages and colors with their current chance for development over the next 2 days. So in this example, there's a system over the Bahamas, near 0% chance of forming in the next 48 hours, but you can contrast that with the disturbance that is out in the Eastern Atlantic near the Cabo Verde Islands that has a 70% or high chance for development in the next 48 hours. Now you can compare that with the 7-day graphical outlook that is showing you that chance of development over 7 days. So some of these systems have a different chance of development when you look at it over a 7-day window versus the 2-day potential. So you've got the same 4 disturbances here, but that system that is over the Bahamas now has a medium chance of development when you look at it over that 7-day window. These shaded areas are showing you that if development is going to occur, the shaded areas are where it's most likely to occur. These are not 7-day track forecasts for these disturbances. That's kind of the caveat when using this product. While you can glean some information about the track forecast or the track movement of these disturbances, you know, we have that one over the Bahamas. It's going to be heading into the Gulf of America. You have your disturbance that's east of the Lesser Antilles, that maybe be in the vicinity of Puerto Rico or Hispaniola. But in terms of, hey, that's a 7-day track forecast, you just can't get that information from this graphic. You instead would need to reference the text product to get you an idea of potential areas that the system will be in over that time period. But you have the 2-day graphic and the 7-day graphic, each covering the represented chances of development over that time. So we'll walk through a quick example here. It's June 15th. You've come into the office for the day on that Thursday around 8 in the morning. The first thing you do during hurricane season every day is you check hurricanes.gov, the homepage, and you see the tropical weather outlook on the homepage. You notice the Hurricane Center has gone ahead and added a new disturbance to the outlook since you looked at it yesterday. There's a new tropical wave that will be emerging off the coast of Africa. They give it a 0% chance of formation over the next 48 hours, but a 20% or low chance for development over the next 7 days. And then that is the potential development area. And by reading the text, you can see that and learn that the system will be tracking west over the next several days across the tropical Atlantic. Because you're a great emergency manager, you even check the tropical weather outlook on a Sunday. Sunday at 8 a.m., you check back in to see an update on this disturbance, and you notice that over the last couple of days, those development chances have continued to increase, and now we are in a high chance for development, both in the 2-day, so over the next 48 hours, 80% high chance of development, and 90% over the next 7 days. So that tells me that we are getting closer to the next tropical cyclone forming and getting advisory packages from the Hurricane Center. Certainly much closer than we were on Friday. Come into the office on Monday. And now you see we are near 100% chance for formation at 8 a.m. And then sure enough, later that morning, actually, we had advisories begin on Tropical Depression 3 from the National Hurricane Center. And this went on to become Tropical Storm Brett as it moved through the Eastern Caribbean. So one last thing to mention on here is if you do notice, again, that tropical weather outlook hatched area is where the system is likely to form, but it is not a track forecast. Once the system developed, that's when we got our actual cone. And you'll notice that the 5-day forecast cone does not match up with that shaded area because, again, it's just showing you about potential development and not a strict track forecast. Lastly, special outlooks. If they do issue a special tropical weather outlook, the Hurricane Center will tell you why. One of the biggest reasons why they'll issue an outlook is because the Air Force or the NOAA hurricane hunters went out into the system, investigated it, and either found that it was developing as expected or not. And the Hurricane Center can provide you an update and then maybe talking about, hey, we may need to issue watches later today if these development trends continue. So I'll launch a quick poll question. Just wanted to gauge with all of you how often you check the tropical weather outlook. It's probably, aside from the forecast cone, it's probably one of the other most familiar products because, again, if you go to hurricanes.gov anytime during hurricane season, it is that static map that is on there on the homepage. So go ahead and answer the poll. We're seeing all of your answers coming in. Looks like most of you at least once a day during hurricane season, if not multiple times a day, pretty much split between those two. And then looks like a few of you, maybe when you just hear about a potential threat to your region. Okay.
So we've just covered when before a system develops, but when it does actually develop, and the Hurricane Center is going to be writing advisories on it, where are you going to get your information? You're going to be going to hurricanes.gov, and the web page is going to be organized something similar to this, where it's going to have the current information there on the left and links to all of the text advisories there near the top. And then there will be little thumbnails that you can click on for the individual graphics. And we're going to go through these text products and some of these graphics in this unit. And so when we're talking about what the Hurricane Center is going to be writing advisories on, we covered earlier about what a tropical cyclone was. So the Hurricane Center is going to be writing advisories on depressions, storms, and hurricanes. But they're also going to be writing advisories on post-tropical cyclones or storms that at one point were tropical and have since transitioned to no longer being tropical, but they still remain a threat to land. So think like a Sandy or a Lee. And so the Hurricane Center is still going to be putting out the same suite of products, and we'll talk about what those are in a moment. And then there's another set of systems. These are potential tropical cyclones. These are actually before we actually meet all those criteria to be a tropical cyclone. So these are systems that do pose a significant threat of either tropical storm winds or storm surge on land within about 72 hours. And that's going to be one of the things that's new this year, is that they've extended the timeline for which they can actually start issuing these advisories on these potential tropical cyclones. It's a really great service enhancement that they've been providing over the last few years. So if we go to the next question, which is really, when is information actually going to be available? Or you're trying to figure out when is a good time for a conference call to coordinate. You want to understand what the NHC's advisory timeline is. And so the Hurricane Center is going to use a very standard set of times: 5 a.m., 11 a.m., 5 p.m., 11 p.m., and 5 a.m. And at each one of these, every 6 hours, when they're writing advisories on a system, they're going to put out a public advisory, a forecast discussion, the wind speed probabilities, your cone graphic, your time of arrival, and potentially storm surge products as well. So again, at 5 a.m., they're going to put this out. And if there's no watches and warnings issued, so it's not near land, you're going to wait another 6 hours before you get a new forecast and a new update. Now, if there is a watch and warning, issued for any land location, it doesn't have to be for the US, then you're going to get an additional piece of information 3 hours after that initial track and forecast update. Just an update on where it is, the hazards, how strong it is, maybe a short discussion about the system and where it's going. And then you'll get your new forecast 3 hours later, and then you'll get an updated public advisory, et cetera, et cetera. So as we get closer and closer, you're going to be getting more and more information. But one of the things that's really important to focus on here is that when we do get those intermediate advisories or those additional public advisories, you're not going to get a new forecast track. You're only going to get a new forecast track at 5 and 11 and 5 and 11 every 6 hours. Now, always is the case, there's always a special circumstance. And just like with the outlook, there is the possibility for an unscheduled update, a special advisory, and these can be issued anytime we have an unexpected or significant change that occurs. So maybe the aircraft went in and found out that the system was stronger, or we have a satellite estimate that indicates this, or maybe possibly the center has formed in a different location, or the track forecast, or it's significantly off track. And then lastly, up until last year, if the Hurricane Center needed to update the watches and warnings, they had to be done on a full package. That has been changed. They can now issue in a slight change to the watches and warnings on intermediate advisories without having to put out an entirely new special advisory.
Thanks, Matthew. And you notice that the battle rhythm for when you have something that's new in development, when you're talking about the outlook phase, when something's just starting to develop versus when you have an actual tropical cyclone that you were getting advisories on, the cadence of products was a little different, but that 5/11 Eastern time is definitely locked in once you get to that advisory time, when you get an actual tropical cyclone. So we'll go through each of these products now. We're going to just jump right into the first product, which is the public advisory. And this is a text product that answers a lot of the real basic questions up front. Where's the storm right now? How strong is the storm? What type of hazards? As you heard from Unit 1, is this going to be a storm surge threat, a rainfall threat, or all hazards in play? And then are there any watches and warnings in effect? So as I mentioned, it is a text product, but I think it's broken up in a nice way where you can skim through and quickly get to different pockets of information when you're searching through this product. So at the start, you get a couple headers talking about, what's the take-home message that the forecaster has put in. And then there's a little summary block with some current information. So in this example for Tropical Storm Mallory, we have its current location about 100 miles off the western tip of Cuba. It's got maximum sustained winds of 70 miles per hour, which makes it a strong tropical storm. Thinking back to the Saffir-Simpson scale, 74 miles an hour is a hurricane. So it's almost a hurricane strength, and it's moving to the north at 7 miles per hour. Now, we have some watches and warnings in effect for parts of the eastern Gulf Coast, from Navarre, Florida to Anna Maria Island, including Tampa Bay has a storm surge watch, and we have hurricane watches in effect from the Alabama-Florida border to the Swanee River, tropical storm watches on either end of that. So we have watches and warnings in place. And if the watches or warnings were new with this advisory, then they would be highlighted specifically as new in that circumstance. If you scroll down a little below that, you get this great discussion or just a little summary section on the current situation overview. This is all plain language typed by the forecaster, and this is a great location to get information if you need to put a situation overview for your sit rep or your IAP, or you need some talking points quickly before you go to a commissioner meeting on just like what's the general overview of the current storm. You can copy and paste it straight out of here. So they usually have a couple lines about where the storm is, what it's going to do in the forecast. In this case, it's going to have a northward motion on the forecast track. It's expected to move inland over the Florida Panhandle or Big Bend on Wednesday. Then it talks about the hurricane hunters have been flying it, and additional strengthening is forecast. And it's forecast to be near or at major hurricane strength when it reaches the northeastern Gulf of America Tuesday and Wednesday. So kind of just gives you that big overview of where the storm is, and from a high level perspective from that 30,000 foot view, what's going on with this hurricane. Then below that, you get your different hazards. They'll have a section on each of the hazards that are a threat with this system. Again, this is meant just to be a quick high-level summary. So storm surge, parts of the Florida Panhandle and Big Bend and the Nature Coast of Florida are going to see 7 to 11 feet. Those are big numbers. That should tell you if you're in those locations, then you need to obviously be investigating the other surge products we'll discuss in a moment. That storm surge is a significant threat with this system. They'll have some lines about wind, rainfall, very similar thing. 4 to 8 inches, isolated maximum totals of over 12 inches in the Florida Panhandle and southern Georgia. So you know that flash flooding is also going to be a threat for this system. So maybe we need to investigate more locally with what the impacts are going to be from the rainfall perspective. So each of the hazards will be listed out here in the bottom of the public advisory. Now, if we wanted to dive a little bit deeper into the forecast itself and kind of see that behind the scenes of, I think a question we get a lot is how confident are the forecasters, or like if this forecast is going to start to change, where might those changes be in the forecast? So if you're interested in that forecast reasoning as well, then you can get all that from the forecast discussion, which is another text product that's kind of a companion and kind of builds on the public advisory. Now, the forecast discussion can have a little bit of some meteorological jargon. They will talk models and wind shear, but there's still lots of plain language built throughout it that I think that anyone who's not a meteorologist can still read the forecast discussion and get a lot of great information they can still take out of it. So in this example, again, we're talking with this building on the same storm here, that when they're talking about the intensity forecast, they're noting that the environment heading into the Gulf is showing that there's likely to be quite a bit of strengthening, and it's a real possibility that we're going to have a major hurricane landfall in a few days. And then when they talk about the track, they notice that all of the models are in good agreement, and they have a fairly confident track forecast. So reading through this discussion, you can kind of take away that, well, we're feeling pretty good about the track forecast. Looks like this is going to be another Florida Panhandle or Big Bend storm, but we're a little uncertain in just how strong it's going to be. We're talking major hurricane, but what's the ceiling and intensity in this scenario? But underneath the forecast discussion, they also will be where the forecaster types up the key messages. You're probably more familiar with seeing this in a graphical format that they share amongst social media, or you can also get on hurricanes.gov. Not every key message will be relevant to your jurisdiction because it can cover international areas. But in this case, bullet point number 3 was everything you need to know is that take-home message for residents in the Southeast US related to, in this example, from Michael. The last portion of the forecast discussion is kind of a quick way to see the actual intensity forecast. For those of you that are familiar with the forecast cone, you know that it shows you, hey, that's going to be a storm or a hurricane or a major hurricane. But if you're interested in seeing those actual forecasted sustained winds, you'd have to go to a place like HurrVac to see them. But you can view them real quick on hurricanes.gov. If you go to the very bottom of the forecast discussion, if you just want to see, hey, what's the strongest storm, what's the strongest winds they're forecasting with this storm? And in this case, at this particular time, it was 110 miles an hour, which again, thinking back to the Saffir-Simpson scale, is just shy of category 3 major hurricane.
So the next product we're going to talk about is the forecast advisory. And this is a text product that you probably don't ever read, but you always see it. And it's going to be the one that answers questions like, how large is the wind field, or where is the system going? It's actually what is going to be being used when you see the map on television from your local meteorologist, or you go into HurrVac and you see the forecast. It is the source for all of the forecast data, and it's what is used in HurrVac. And the way it's broken up is there's a section about, say, like the current wind radii. It's got information about what the forecast wind radii are, or sometimes it'll include information about how large the eye is or what direction it's going. You see that up in the top, or the central pressure. But one of the questions we want to find out just here is, when you see this graphic on the map, that blue area that's around Cindy, what is it actually representing? Is it that tropical storm winds are occurring everywhere in that blue area? Is it the area of 2/3 chance of experiencing tropical storm winds? Is it the maximum extent of tropical storm winds? Or is it the area where hurricane winds are occurring? So just letting y'all provide your answer real quick. It looks like about a quarter of you are saying maybe 2/3 chance of experiencing tropical storm winds. About 4 in 10 saying about the maximum extent, and almost equal between everywhere is getting tropical storm and hurricane winds are occurring. So the answer is actually it's the maximum extent of where the tropical storm winds are occurring. So let's talk a little bit more about that. So when the Hurricane Center actually is making their forecast, the size of the storm, they're actually providing their forecast for their wind radii in the 4 quadrants. So how far do the tropical storm force winds go out to the northeast, to the southeast, to the northwest, to the southwest? And, one of the things to be aware of is that it can be an overestimation when we're close to land. So here's an example. For the forecast, if there are hurricane force winds, it'll include the 64 knot wind radii, the 50 knot or the strong tropical storm radii, or the 34 knot or the tropical storm radii. And so in this case, the tropical storm radii go out about 130 miles to the northeast, 150 to the southeast, 90 on the southwest side, and 120 on the northwest side. But you probably have seen this in a program like HURVAC, or if you saw it on television. And when you see it, it looks like the winds are everywhere because of the way it's being colored in. But that is really just the maximum extent. And when you look at the table on the right-hand side there, what I want to reinforce is that the Hurricane Center is making a wind radii forecast for tropical storm winds out through the entire 5-day forecast. The 50 knot winds, or the strong tropical storm force winds, they're also forecasting out through 5 days. But the hurricane force winds, they're actually only forecasting out through 72 hours or 3 days. Now, this graphic, I think, is something that most people have seen, the error cone. It's used a lot, both on television, but people see it on the website. And it is a situational awareness tool. It provides information about the forecast. It's been amended a few times over the years to add additional information. But I want to ask the question if folks understand what we actually use to make that size of the cone. So what is used to construct the size of the forecast cone? Is it representing the impact areas? Is it the size of the wind field? Is the size of the cone based on the model spread? Or is it the past 5 years of forecast error? So we'll give you a moment or two to put in an answer. People are continuing their responses. My eyes are old, so it's hard for me to see this. But it looks like about 1/3 of you are saying the model spread, about a quarter saying impact areas, and a little under a quarter saying the past forecast error. So the actual answer, let's go through this. So the possible impact areas. If you look at the graphic, you see that orange area is the current wind field. And so you can already see that the wind field itself is outside of the cone, as well as the watches and warnings are outside of the cone. So it's not going to be the impact area, and it's not going to be the wind field. I wish the cone said something about the current model spread or current uncertainty. In fact, the cone size is really just a function of the past 5 years of forecast error. It's going to be the same for all storms in a given year. And we'll talk a little bit more about that tomorrow when we talk about historical track errors of forecast uncertainty. But just suffice it to say that when you do see the cone, understand that the cone is going to be the same for all storms in that year. And it's trying to represent the probable track of the center, not the impacts. In fact, based on how it's being drawn, 1/3 of the time, the center of the storm, by design, would be outside of that cone. And that's not even just the impacts are going to extend far beyond that, but the center itself is by design is to be outside of the cone 1/3 of the time. So what is the cone good for? It's a situational awareness tool. It's displaying information about historical track uncertainty, but it doesn't necessarily communicate about the hazards. And it's important to understand when you're communicating to people that it is not, they shouldn't be evaluating their vulnerability or the threat simply based on this. However, one of the things that the Hurricane Center added to their product suite last year is a new experimental product, where on the left-hand side, you see our legacy or traditional cone, which shows the coastal watches and warnings. And then on the right is a graphic that shows the extent of the inland wind watches and warnings. And it is certainly much more communicative of the potential hazards when you see the cone displayed like this. And this is something that they've been experimenting with, and I think has been extremely successful in terms of communicating that inland hazard.
So if the forecast cone is maybe not the best for making those tactical decision making, then what other products should you be using? And we're going to introduce a few of them. One of them, for as far as like a wind perspective goes, is the wind speed probabilities. If you have a specific location that you're looking at for a staging area and you want to know what the risk is at that location from the wind, you want to just know what the general chances are of seeing some effects at your location, and you're interested in the wind timing. The forecast cone was built around where the center of the storm is going to be. So those dots are where the center is. And we know that the winds and the rain and the storm surge are going to begin well before the eye of the storm arrives. So the wind speed probability products can be used to help answer all of these questions. Now we're going to get well into wind speed probabilities tomorrow afternoon and how they're created. But just as a brief introduction, the wind speed probabilities have a text product and a graphical product. The text product just provides you some select locations, usually the bigger population centers along the coast and some inland. And they will provide wind speed probabilities for tropical storm force winds. So your 34 knots, 50-knot winds, or we refer to them as the strong tropical storm force winds, that converts to about 58 miles per hour. That number may look familiar if you're aware of severe thunderstorm warnings. They use a similar threshold. Generally, once we start seeing winds of over 58 miles per hour, it's usually tied to more notable damage. So we provide, the Hurricane Center provides wind speed probabilities there. And then 64 knot, which is your hurricane force winds. So each of these wind speeds get probabilities forecast from a model at the Hurricane Center for select locations. And then those correspond to a graphic. And they provide a graphic for those same three thresholds: tropical storm, strong tropical storm, and hurricane force winds. Now, what is shown in the text product and what is on the graphic is going to be identical. They are one in the same. The text product can provide you with probabilities within certain time windows, but if you notice, there's certain numbers that are in parentheses, and that's sort of your total risk over those 5 days. They adding up all of the numbers. So the graphic is showing you what the total probability is of seeing winds at over those next 5 days. And as you can see, each of those total numbers in the last column matches up with what is being shaded here on the graphic. So if you were to view them in HERVAC, is an even better way to interact with those graphics and look at specific points. But we will talk even in more detail about how those are created and can be used tomorrow afternoon. Those wind speed probability model data can also be used to provide timing information. And the Hurricane Center provides the earliest reasonable arrival time of tropical storm force winds, and most likely. First, we'll discuss earliest reasonable. They'll provide a graphic that's contoured around 6 or 12-hour intervals to show you when the earliest time that tropical storm force winds, sustained winds, could arrive at that location. The earliest reasonable can be defined as the 10% chance of onset, meaning 10% chance that it's going to occur earlier than what's on the graphic. So it's a very conservative time. And you have to remember that it's associated with probabilities with this contour. So it's not saying that everywhere here in this outlined area is going to see tropical storm force winds, but if they were to occur, and there's a probability associated with that, but if they were to occur, then this is the earliest reasonable time that they could happen at. And that gets contrasted with the most likely, which is you're equally likely to occur earlier or later. It's sort of your best guess. Typically, if I get asked, hey, what time is the tropical storm force winds going to arrive in this location, I will provide the most likely. It depends on, as far as which graphic you use, depends on the decision you're making. How many buffers do you have built into your plan? If you have lots of buffers already built in, do you need to add an additional buffer by using the earliest reasonable? Maybe, maybe not. And also, if you're communicating with the public, the earliest reasonable is kind of that be ready time for the public. Most people in the public, I would say, probably don't have lots of buffers built into their plan. So maybe communicating to them that earliest time, whereas internally within, the EOC, the most likely time is maybe, and in that case, a better estimate for us for when that. But it depends on the situation, depends on the decision you're making, is if you need extra buffers built into that. And again, there are probabilities associated with this. So for example, if we were going to look at this graphic and we'll look at New Orleans, they've got about a 10% chance of seeing tropical storm force winds. And if they were to occur, they're most likely to occur, or to start, most likely to start Tuesday night. But that's, even though Apalachicola has a very similar time, late Tuesday night, for when tropical storm force winds could begin, they have a much higher percentage, almost over 90% chance of seeing tropical storm force winds. So I encourage you, when you're looking at this contour, to keep in mind that there are probabilities associated with that. And then we'll jump into watches and warnings as another way to help you identify the hazards. The Hurricane Center provides, or is the issuing authority for storm surge related watches and warnings and the wind watches and warnings. And especially for the coastal areas. So those watches and warnings are there to help answer the questions of which areas are greatest for concern, and also kind of help you outline the timing of when the hazards could begin. So we'll start first with the storm surge side. Storm surge watches, which is saying that there's a possibility of seeing that life-threatening inundation, they are issued generally within around 48 hours before that potentially life-threatening inundation arrives. And then the storm surge warning kind of increases that confidence in seeing that life-threatening inundation. And then we're also closer in time. So we're about 36 hours out from that storm surge threat. When storm surge warnings are issued, they do activate WIA. So as soon as that's issued, when that 5 o'clock or 11 o'clock advisory comes out, then that will go ahead and trigger the WIA alert to the public when you jump to the warning. It's a very similar timeline for the hurricane side. Hurricane watches are when conditions are possible in about 48 hours. And then warnings are issued when hurricane conditions are expected in about 36 hours. So again, you'll notice there's a little bit of a difference in confidence level in the hazard happening, but also the timing. We're now closer in time to the hurricane conditions. Just like with storm surge, hurricane warnings activate WIA. So as soon as those advisories and the warnings are issued, again, the public will get that WIA alert. Just to mention that the hurricane watches and warnings, those 36 and 48-hour timelines, are based around when tropical storm force winds begin. And I can kind of reference that back to the wind speed probabilities. As emergency managers, once sustained tropical storm force winds start in our community, I'd wager that we want the public off the roads, the evacuation's completed, folks in shelters. We're going to start locking down bridges, start shutting down the community when you get winds to that threshold. So that's really why, as most decisions are based upon that wind threshold. That's why the Hurricane Center kind of bases everything around that. They're telling you when tropical storm winds are going to arrive. And that's also really when they're basing the timing here for the hurricane products. So we'll walk through a quick example, some screenshots from HurrVac from a past storm. You can see that you've got your wind field plotted here, and the forecast cone, we have a storm approaching Louisiana. In this case, the coast of Southeast Louisiana is about 36 hours out from seeing tropical storm force winds. about 36 hours means we're in the warning phase, right? 36 hours out is for the warnings. So the Hurricane Center is going to issue some hurricane warnings for a portion of the coastline. So you can just think, where would you issue those hurricane warnings? This is the forecasted size of the storm with the wind field, but it's a perfect forecast. We're assuming it goes right down the middle of the forecast cone, and it is perfect in this scenario. So you would say maybe okay, we definitely need hurricane warnings for that central part of the Louisiana coastline, but what if there's error in the forecast? We know there's historical error, just based on the forecast cone, and maybe in this scenario we have even more model uncertainty in the track. So this is where one of the forecasters wanted to issue hurricane warnings in this scenario. So you can see the entire coastline of Louisiana and Mississippi, and even a little bit into Alabama. It might be a little bit far to the east, but certainly into Mississippi. So if you were to shift that storm to the eastern side of the forecast cone, then it would be tracking over New Orleans area, and you would certainly see hurricane conditions in coastal Mississippi. Same thing if you shift that to the western side of the forecast cone. So the watches and warnings will be issued for the areas that the forecasters are most concerned with seeing that threat, and it is going to be, of course, taking into account some uncertainty, because not every forecast is going to be perfect.
So let's circle back and talk about when these forecast products are routinely issued. So how often is a new NHC track and intensity forecast going to be routinely issued? Is it every 3 hours? Is it every 6 hours, every 8 hours, or only when there's a change in the models? And so I think the vast majority of you are answering 6 hours, which is correct. Some of you identified 3 hours. That is when we get the addition of the intermediate public advisory. So let's talk a little bit about that. So just to repeat that when there are no watches and warnings, you're going to get a suite of products, a track, public advisory, the discussion to explain about the how and the why of the forecast, the wind speed probabilities, timing information, storm surge products. You're going to get those at 5 and 11, 5 and 11 Eastern. So for Central, it would be 4 and 10. And when there is a watch and warning in effect, you're also going to get the addition of the public advisory to update you on the hazards, the location, just a description of what's going on with the storm. And so this is basically what the intermediate public advisory looks like. It's very similar to what you would see when the full package comes out. There may be now some changes to the watches and warnings. Again, that was something that was changed last year to allow the Hurricane Center to update these changes for U.S. locations. But it's very similar to what you would see with the regular public advisory. However, there's one more piece of information that when we get close enough to land that we can actually track the center on radar, you actually will get hourly information. Tropical cyclone updates will be issued every hour. If it's not a public advisory, the intermediate, or the full package, you're going to be getting a TCU or a tropical cyclone update, which, as we mentioned, as we get closer and closer to the actual incident, you're going to get this constant flood of information that's going to update you. And the TCU is kind of like the utility player in baseball. It can do pretty much anything. It can alert us to when the cyclone makes landfall, can tell us about changes, but it's also the product that they're going to use to provide those hourly estimates when it's close enough to land and we're trying to keep that constant flow of information. So we talked earlier today about the hazards, and really it's the hazards that as emergency managers you're responding to. So you want to know what areas could flood or how high the water could get, or a reasonable worst case scenario. You're going to be looking at those storm surge products. And so The storm surge unit is going to be providing a graphic like this to provide the potential for storm surge flooding. Now, this graphic doesn't represent a flooding footprint. It doesn't mean that everywhere there are colors there that that's going to be flooded. It's actually kind of like the wind speed probabilities, where it's a point-based forecast. So at any given point, that is a reasonable worst case scenario. And we'll talk a little bit more detail about this. It's providing you the height above ground that the water could reach. So it's a reasonable worst case scenario. The values have a 10% chance of being exceeded, or there's only a 10% chance of it being higher than that. So it's a reasonable worst case scenario. It's issued up to 72 hours before the potential storm surge threat. And it does take a little bit of time to produce this, so it might be available a little bit after the advisory, maybe up to an hour after the advisory is issued. The next storm surge graphic is something that you're familiar with, in that I suspect when Michael talked about the public advisory, that list of values, this is a graphic companion to that, which is really great, because what they're doing is they're taking those values that you see in the public advisory, and they're plotting it on a map so that visually you can see where those peak values are. So it's the expected inundation along that immediate coast, those maximum height values above ground. And as I said, it's going to mirror what's actually in the public advisory. It's something that you can use and display in your EOCs. We include it in the emails we send out. This becomes available when watches and warnings are in effect, and it's generally available at the same time that all the other products are released, like the cone or the wind speed probabilities. It's available with that main suite of products. So we also heard about inland flooding or freshwater flooding, and if you want to know about how much rain is forecast, or what areas could see the flash flooding, which day is the greatest risk, these are going to be the rainfall products, the products from the Weather Prediction Center. And most people are familiar with something that looks like this, where it's showing you, in this case, it's like 10 to 15 inches of rain, which is useful information. But what's really useful is to understand whether or not that rainfall is going to cause flooding. What is the risk there? And this is a really great resource, not just for tropical incidents, but also all year long. It's a really great resource from the Weather Prediction Center, and it tells you whether or not you have a high chance of seeing the flash flood, exceeding that flash flood guidance. And those days when we do have a high, they matter. They typically are about 4% of the year, so it's not very often. And it includes all incidents, tropical and non-tropical. And they've done the research, and during high risk days, almost half will have at least one fatality, and well over a half are going to have $1 million or more just in damages. And so the high risk days actually account for over 80% of all flood damages. So this is a really great resource available for you to use during these incidents, but also outside of hurricane season.
So that covers all of the products that come out of the National Hurricane Center and their other the other NOAA national centers, like the Weather Prediction Center. And all of those graphics and products, text products, you will find on hurricanes.gov with that area specific to that ongoing storm. But we wanted to take a couple minutes to at least touch on a few things that are unique to what may come out of your local weather forecast office, for those of you that are at the local level, and some of the states as well may be using some of these products. So if we're trying to localize the impacts, which is what the local forecast office is going to take the 30,000 foot view of the track intensity, wind speed probabilities, and then help dial that down to the local level. They'll provide one product called the Hurricane Local Statement. This is a text product. It mirrors a lot of the information you may see in something like the public advisory, but it's typically much more detailed and it's specific to that jurisdiction, typically at the county level. Sometimes the counties are split into multiple areas, like maybe a coastal part of the county and an inland part of the county. But each of them will have their own hurricane local statement, and it will provide everything that you need to know, all of the watches and warnings, all of the hazard and timing information specific to that locality. So if you're really trying to see things locally in your community, then the Hurricane Local Statement can be a great summary product from your local forecast office. The local offices also help create something called the HTI, or the Hurricane Threats Impacts Graphic. You have to go to your local office's webpage. They typically have their own tropical page to access these graphics. But they are a different way to look at some of the other data we've shown here. We share this for two reasons. One, because sometimes to have all of the main 4 hazards shown under the same kind of general color scale and threat levels of a elevated, moderate, high, extreme, you've got the same 4 colors across the 4 hazards, so it looks familiar when you're trying to compare each hazard. Can be helpful for a briefing or something at the local or the state level. But typically what you see here for like the storm surge graphic for HTI, you're going to see the same types of numbers and outlines as you would if you were looking at the peak surge graphic, or the inland flooding compared to the excessive rainfall outlook, that ERO graphic. It's not going to show you new information. It's just going to show you it in a different scale and a different color pattern. Maybe the only caveat to that is the wind. The local offices will highlight areas that have a potential for seeing major hurricane force winds over 110. If you think back to the wind speed probabilities, there wasn't a wind speed probability for major hurricane force winds. And if you're interested in seeing which areas have that potential for seeing major hurricane force winds during a major hurricane, the HTI through your local office can help you identify the areas that have that potential there. And then lastly, they have something called the extreme wind warning. This is a short fused warning product that is issued when the eye wall of a major hurricane is making landfall. So you're having a category 3 or greater, so winds 115 miles an hour or greater sustained are anticipated. They're coming on shore, and it's kind of like this is like your last warning, and it's intended for the public to do that shelter of last resort, hunker down, kind of taught like a tornado warning, because you're about to have extreme destructive winds that are about to move through the community. So they'll issue these extreme wind warnings with a little bit of lead time, 20 minutes, an hour before these eye walls come on shore, and they're short fused to kind of give that last notification to the public. When these go out, it does activate the WIA. So just like a tornado warning does, with similar types of language to get folks to shelter away from windows, interior rooms, to ride out during the eye wall passage.
So we talked about the actual timeline of products and when MHC is going to be issuing them, but I think it's also really helpful sometimes to see how these products fit within our own plans. So this is an example from FEMA Region 4, from their regional all hazard plan, and they have their normal operations. Their elevated threat is when hurricane season begins. Credible threat is 72 hours, etc. And so for them, they consider that the hurricane evacuation studies, which you're going to hear about tomorrow, are a resource that they can use all year long. So normal operations all the way through post-landfall. And then things like HAZUS is something that they would only be able to use closer into the start of the impacts. The tropical weather outlook, as an example, that becomes available once hurricane season begins. The actual 5-day forecast from the Hurricane Center is between elevated threat all the way through post-landfall. And as we get closer in time, some of these certain ones of these products are then used. I mean, like the rainfall forecasts that go out 3 days, and then flash flood warnings once we actually start to see that rainfall hitting the ground and the response of it, and then river forecasts and flood outlooks, et cetera, et cetera, et cetera. And all of this, again, as we talked about, when we're many days out, there are fewer products, larger uncertainties, but as we get closer and closer to the actual incident occurring, there's going to be this constant flow of information, more detailed products, all the way through the actual impacts of the storm. And so with that, I will ask if there are any questions about this unit. Doesn't look like there are any.
Looks like they've all been answered, but I'll ask if Zane or NHC had anything that needed to be elevated for questions. It looks like they all got answered.
Yeah, thank you, Matthew, and thank you, Michael. No questions at this time, but if you have additional questions, please feel free to put them in the Q&A box and we'll answer them there or flag them for the presenters.
Okay.
Over.
So just to sort of close us out today, so we covered the basics of hurricanes. We covered the hazards in detail. We just finished talking about where you're going to get your information. Tomorrow, when we reconvene at 1 o'clock, we're going to talk about the fact that there is uncertainty in every forecast. I mean, as I said before, as an emergency manager, you don't have the luxury of waiting until it's going to make landfall to make your decision. You have to make decisions with uncertain information. But the good news is that we have resources to help you. So, you know, Michael talked about the wind speed probabilities. You're going to hear a lot more about that tomorrow. You heard about how sensitive storm surge is to, you know, all of those parameters. So we're going to learn about the way that we use those to forecast or to be the basis of our storm surge for the evacuation studies. And there's all kinds of resources that are available. And then when we finish it out, we're going to talk about how all of this information can be used to help you as an emergency manager make better decisions. And that starts with better data and better information and the planning process and being informed and knowing what to look for and what information. So, you know, we spent a lot of time this afternoon going through those advisories so that we could point out to you where to look in those to find the information. So tomorrow we'll start back up at 1 o'clock with that. Did it sound like Zane had a question or somebody? No? Okay, just my imagination. And I just want to reiterate that for those of you, everyone who's on today registered through Zoom, but not everyone who's on today has registered and submitted an application to NDEMU to get credit. If you want to get credit, we would encourage you to do so, to use the link to submit an application. Again, the course code is SL05M. And once you do get accepted, they will ask at the end of it to submit an evaluation. So with that, anything else?
I think that's all we have for today. We'll stick around for those of you that have a couple questions about submitting the NDMU application. We'll see a few questions, but we'll stay on the call for a few minutes to continue to answer any questions anyone has. But otherwise, you are all free to drop, and we'll reconvene tomorrow at 1 p.m.
Thank you all.